mean, everybody, I think, has different words that they use to describe it, but it's just the sense, like, I can feel it in your heart, like something good in the world's happening.
Hey, everyone. That is Desiree Tullis, a professor at Oregon State University who's been studying the impacts of the biggest dam removal in U.S. history. The removal project unleashed the Klamath River from 4 dams that blocked fish passage for more than 100 years. In this podcast, you'll hear more from Desiree about the experience of watching the river transform and what they are learning. I began following the story in the summer of 2023. It started with a road trip.
I love that. That's one of the things I love about Eastern Oregon.
Really?
That is Desiree and 2 Oregon State University engineering students, Whitney and Grace, headed out to do some field work in Northern California. Like any summer camping trip, there is an air of excitement for getting outdoors on a mini adventure. I'm Rachel Robertson, and this is the 3rd episode of the season on the Klamath Dam removals. In this episode, we'll get in the river with the ecological team studying the impacts of the dam removals on algae and aquatic plants. From the College of Engineering at Oregon State University, this is Engineering Out Loud. The highlight of the first night was a short walk from our campsite to a perfect swimming hole in Dillon Creek. We were joined that night by graduate students Christine Alford and Brooke Thompson. Early the next morning, the team of 5 women headed to the first site and started work. The loud noise you hear is Grace pumping up a kayak to carry equipment to the other side of the river.
Okay.
The rest of the team sorts out who is doing what.
Do you want to be in the water or not?
I can be in the water. I don't mind that.
All right, so do you want to measure velocity and light? That's a easy entree into the...
Okay. We can switch off too.
The team is getting ready to collect samples at several sites in the river and take measurements of the conditions and habitat features that could impact plant and algae growth. It was 2 full days of work, taking samples at 80 to 100 nearby locations each day. Desiree describes the experience as literally immersive.
There's a lot of snorkeling involved because you got to get down to the bottom of the river to see what's growing there. And so in the shallow areas, you can do it just by looking through the water. But when it gets deeper, you have to dive down and measure how much of different types of algae are there and the different types of rocks that are on the substrate or the bottom of the river.
You can hear Grace in the background calling out what she sees on the riverbed to Brooke on shore, who's taking notes. Before we get into exactly what they're doing, I wanted you to hear from Desiree about why they are doing it.
Algae underpin a lot of stuff in the river in terms of oxygen for fish. They clog boat motors, tribal fishing nets, but they also connect to other parts of the ecosystem like disease risk. But they're just really poorly understood. So we're doing really basic science just to understand some, the hydraulics and sediments is a big driver of these algae, which is sort of where my expertise and interests come in. But it's fun to see it connect to so many different other things that people care about.
Desiree's area of research is water resources engineering, but the team also includes experts in microbiology, fisheries and wildlife, and ecology. The collaborations are enabling them to be comprehensive in their research.
We, as a group, we are mapping how much of the different types of algae are here in the habitat that they're occurring in. And the types of the habitat features we're interested in are things like what they're growing on. So is it rock? Is it bedrock, or is it gravel or cobble, or is it just sand? We're interested in what depths and velocities it's growing in, and we're also interested in how much light they're getting. Our hypothesis is that they are influenced strongly by the velocity that they're growing in and also how much light is available to them. And so maybe nutrients matter less in the Klamath because there's so many nutrients, it's nutrient rich. But that's something we're trying to sort of disentangle. There's a lot of connections that aren't really well understood.
Oh, it's good. Okay. Tell me what you're doing. I am hammering rebar into the riverbed that'll allow us to take coarse particulate measurements in the river. We set a net up on this rebar and then let it sit in the river for a while and see what we catch.
That is Grace Boyson, who had just finished her bachelor's degree and was working on her master's. In addition to setting up the net to collect particulates in the river, the team also took velocity measurements next to the net.
All right, this one's 1.021.
Whitney Packard was taking the velocity measurements at this particular site. Whitney was an undergraduate in ecological engineering at the time. Once she waded back to shore, she explained to me what she was doing.
So I just took the velocity reader out into the water to measure the velocity at different points on the net that we use to take the sea palm samples. So we take the velocity at river right, river left, in the center, so we can kind of tell across the gradient how quickly the water's moving. And then using those velocities, we can tell kind of the rate at which different biomass and other things in the river are flowing into the net.
CPOM stands for coarse particulate organic matter, which includes plants and algae. The samples from the net were labeled and stored to take back to the lab, where Whitney would filter them, dry them out, and measure how much organic material was in each sample. It's the kind of experience that brings science to life for the students.
We talk about turbulence, we talk about the different flow features in rivers, and students don't get it until they see it. And so even now, like they're using language that they learned in class, and they're seeing it in the real world. And I think that's just so important, so that they're not designing something with no awareness of like what the numbers actually mean. But it also, I think, establishes like passion and motivation to continue doing the work, because most of the people who are in this field don't want to just sit in the office all the time.
On the second day, the sites were located near the former Klamath River Community Hall that was destroyed by wildfire in 2022. The team picked that location because variations in habitat supported a much more diverse community of algae than the other sites. I stood with Desiree next to the river in a post-fire debris flow, and we looked at the devastated landscape that included what looked to be parts of cars and farm equipment half buried in the mud. She told me more about what can be learned at this site.
The thing that stands out to me about this site is just how much it's been impacted by the wildfire. And I don't know how many people really appreciate the impacts of wildfire on rivers and the landscape. It's pretty profound. I mean, none of this was here last year. It all was this debris flow that came out of the tributary, and it radically changed the river. And so that's the thing that stands out to me. And also, all the dead snags everywhere. It's definitely already a system undergoing a lot of change. And I think that's what we're facing in the future, right? Like there's no steady state anymore. Everything's kind of constantly being disrupted and changing. And that's one of the things I think I really like about ecological engineering, is that we are designing with systems in mind, and systems that are open and are changing. And so I feel like the students get a lot more exposure to those kind of concepts and ideas and models and tools than I did as in my background as a civil engineer. It was very, bridge oriented. You've got a set of loads going across the bridge, you apply a factor of safety, everything is steady, but in ecosystems, that's not at all the case. And so the students have tools to sort of understand that. The world's changing, how do you design for a changing world?
When you think of engineers, you don't normally imagine them standing next to a river in a wetsuit. I asked Desiree to explain how this project is engineering.
Yeah, that's a good question. And the way I think of ecological engineers is we're kind of like maybe a part of a hub on a multi-spoke wheel. We're still problem solvers, we're still engineers. I'm licensed as a civil engineer. My expertise is in fluid mechanics and sediment transport and river infrastructure like dams and dam removals. And all of this, and if you ask me, all of what's happening here is all like a hydraulics problem. It's these algae are here as a function of both the depth and velocity that they're experiencing and the sediment load coming down the river, as well as some water quality changes. So I see these like the physics of the flow driving what's happening, and then what's happening is what other people care about. So nobody really cares about the depths and velocities, but they care about the algae. And so I see, especially in ecological engineering, like we're studying the physics, but it connects to things that people care about. And so that's why I think ecological engineering is so fun, because we get to hang out with biologists. I get to go whitewater rafting, to do field work. I get to do these things with anthropologists and other people who really understand how the world works. And I'm still grounded in my expertise, but I can apply it to things that are societally relevant.
In the evening on the second night, we were hanging around at the campground, and I got a chance to talk to Whitney and Grace about what they learned from working on the project.
This is actually my first time doing field research, so I wasn't really sure what to expect, but having the opportunity to research truly in the outdoors is amazing. It's a lot different than lab work, which is something that I was more used to. I love feet in the river, hands dirty. It's like feeling science, which I really love. the Klamath Dam removals, since it is the largest dam removal in history. I think it's really amazing to have even a small part in something so big. And also, I think conversing and learning from the tribal members who are involved in this process is extremely valuable. It's been so much fun to watch people like Desiree work, who is such a great role model in terms of being a woman in engineering. And she's obviously very dedicated to not only this river, but also the research that we're doing. Learning from Grace, who's a master's student in my program, is very exciting. There's just a plethora of opportunities, which is really amazing.
It seems like you are all pretty close. I mean, it's been fun hanging out with you. That was Whitney Packard, who graduated last June with a bachelor's in ecological engineering and a minor in horticulture. She is now a water planning engineer for Herrera Environmental Consultants. I also talked to Grace Boyson, who already had tons of fieldwork experience, but none of it on a river.
I think rivers are a really crucial part of the Pacific Northwest and just in general of any ecosystem that they're in the landscape of. And I'm really interested in working in river or wetland systems professionally in my career. And so I think I was just really excited about I'm bringing copious amounts of field experience from inland in the Cascades and in the Deschutes and in more forested systems to my personal experience with rivers into this. And so it's letting me gain some skills that I definitely had the seeds for, but I never really gotten to grow them in undergrad. So I'm really happy I'm getting to do that. And it's also just so cool to hear all the different people's stories and expertise on the project. It's just so neat to be a part of, and it's a lovely breath of fresh air to be with an awesome crew that's just dedicated to, do the best work they can.
Grace completed her master's in ecological engineering and is putting her experience to work as a water resources engineer in training with Interfluve, an engineering consulting firm in Hood River. Desiree made sure as many students as possible got to experience this historic dam removal. In addition to the students who worked on the research, Desiree's river engineering class toured the dams before they came out and got a chance to speak to the landowners, tribal members, and scientists working on the river. I spoke again to Desiree earlier this year after she had time to reflect about her discoveries on the river. She had just uncovered a thank you card from her class and was struck by how many of her students talked about it as a transformative experience.
Seeing a place when it's undergoing change helps them with their own identity. It's a fun thing for them to talk about. Everybody likes to talk about it, but I think more importantly, there's this identity thing where they're part of something bigger. Seeing a space as it's undergoing change, the landscape, this place they care about, and the reflections that they do about their own lives and about themselves and their careers, the motivation to do good things in the world. I think that all materializes when you spend time in a place. And I think that's probably been, aside from the technical skills that we all get, I think that's been the most important part.
At this point in the project, the 4 dams have been removed, and the restoration process has begun. I asked Desiree to tell me what it was like to witness this historic dam removal and what they've learned so far. How soon after the dams came out did you go back, and what was it like?
Well, I'll say that the dams coming out was not a binary, like they were in versus they were out. I was there many times through the process of them draining the reservoirs, and for me, that was maybe as important as seeing the actual dams gone. There were these phases. And so the first time I was there was the week after drawdown began. We were working in the middle of the winter, collecting water quality data, and starting to see those reservoirs contract was this first sense of excitement and hope and optimism. And then going back on a pretty regular basis and seeing the reservoirs then drained was another sort of phase. And then there was a phase of where the vegetation started to come in. And it was really, everybody I think has different words that they use to describe it, but it's just the sense, I can feel it in your heart, like something good in the world's happening. But then as you go downstream, you also see, the impacts of that. And I think I was surprised, even though I had modeled the sediment transport in that river, should have had really clear expectations. And I did, but then when actually seeing the sediment deposited along the river, these swimming holes we used to play in were filled with sediment, there was a little bit of disappointment, a little bit of surprise, even though I know I shouldn't have been surprised. And then just the curiosity of, well, how long is this going to take to recover? What is the transition trajectory from here? It wasn't just this binary of sort of they're in and then they're out. It was really this transformation over time.
Yeah, so you mentioned that even with all the modeling you have done, you were still kind of surprised. And so I want to talk about the data a little bit more. What have you found so far? What has been surprising to you?
I think on that side of things, we have some, fun for me anyway, observations, particularly around the plants and algae, which we've talked about a lot. Because last fall, before the drawdown began, we were sitting around planning the following summer's activities, and we were all worried there wasn't going to be any plants or algae in the river. And we literally were talking about Plan C and Plan D for Issy Tang. She's the master's student leading that part of the project, because we thought, well, there's going to be nothing growing in the river. What project is she going to do if there are no data? And so I was a little surprised to show up in early June, and the river was just covered in plants and algae. And because we had this expectation, right, if there's a lot of sediment in the river, there's not going to be any light in the river when plants need light to grow. That was our hypothesis. And then we show up and there's a lot of plants and algae everywhere. And so it really forced us to reckon with how we'd been wrong, and our hypothesis maybe had been wrong, and really reevaluate what might be driving those dynamics. And so I think, at least how we understand it now, is that discharge or flow in the river is really the primary driver. So what happened last winter is they held like high flows back because they were doing construction, right? They didn't want any big floods coming through during construction, but those floods are necessary to move the bed around. They mobilize the riverbed, and when they do that, that rips out the plants and the algae. And those big mobilizing flows didn't ever come, and so those plants more or less sort of overwintered. And those floods are really important for resetting the river. And that finding has really helped us look beyond the Klamath, because there's a lot of rivers across the American West where we've eliminated floods, and we're seeing plants and algae expand. This is just one example of where we were surprised as scientists, and we thought light was going to be the driver. And it is important, but it's more as a secondary driver. But then also this relevance of what's happening in the Klamath to all these other dams and all these other rivers across the American West.
One of the most amazing things that happened after the dam removals was that the Chinook salmon returned to the Klamath Basin for the fall run. That hasn't happened in over 100 years since the first dams were constructed. In fall of 2024, the fish were spotted spawning at a Klamath tributary upriver from the former J.C. Boyle Dam site. The river was murky with sediment. It is often described as looking like chocolate milk.
I think there were a lot of folks surprised that the salmon navigated up through that chocolate milk and made it back above the dams that were spawning literally within weeks. I mean, there's so much optimism around that. And I suppose we probably shouldn't be surprised. These creatures are resilient, but it's just one more case study, one more story helping us see that if we just get out of the way, these ecosystems can recover. Well, I should say they can persist, because there is a difference between persisting and thriving.
The salmon return was a pretty dramatic change, but not what Desiree's research was focused on. So I asked her what changes she saw in her work.
There have been a lot of changes. Some of the changes that we've been trying to document around things like water quality, like dissolved oxygen. It changed a lot in the river. What are the mechanisms for that? And that's one of those things that I think is really neat, because it's not just about the Klamath. Christine Alford is the student leading that, and she's just created this really neat project around understanding how carbon and sediment in the river impacts how much oxygen is in the river. And that's something that's related to climate change. It's related to wildfire. So this is another space in which the Klamath is sort of giving us all kinds of new knowledge about how systems, these ecosystems and water quality works. So we did see some patterns in dissolved oxygen changes, but they were really mild relative to what everybody was worried about. So that was a positive, I think. It was really interesting to witness local residents and how their perceptions of the project has changed. I find myself really drawn to the sediment story and how the deposited sediment is moving and evolving, and how the plants are colonizing it, and those interactions between like the hydraulics of the river and the ecosystem parts. But for me, I think one of the most important changes to witness was in myself. I have just learned and grown so much over the past 3 years of this project.
And some of that learning has been on reciprocity and collaboration, particularly with the Karuk and Yurok tribes. Some of that has been learning about how to be a girl boss, learning how to stand up for myself and for my students and others, and to do that in a way that's productive and for which I don't feel ashamed afterwards. And then some of it's just basic learning, just sort of the basic science. For example, Laurel Genzoli is a postdoc working on this project, and I've just learned so much from her about how energy translates through the food web. And that stimulated my thinking on whole other sets of scientific inquiries. So in terms of changes, the river's changed, and I think we have changed. And that's kind of your best hope for, I think, any kind of big project, is that it impacts you as much as, you're hopefully contributing back as well.
Thanks for listening to the third episode of this season on the Klamath Dam removals. I want to thank Desiree for her engaged collaboration on this podcast season. Thanks also to Steve Franzel, Chris Palmer, Owen Perry, and Duncan Robertson. You can find bonus content and the full transcript at engineeringoutloud.oregonstate.edu. Have you seen the salmon?
Yes. Yeah. Yeah, it was, they looked pretty haggard by the time they got up to Spencer Creek, but it was pretty profound.